Tonight, we're going to explore something that sounds deceptively simple, almost like a trick of perspective, but is, in truth, one of the most staggering concepts ever confronted by science: what lies beyond the observable universe. You've probably heard the phrase before, maybe in a documentary, maybe in a late-night conversation about space, or maybe whispered as a cosmic riddle with no answer. But here's what most people never truly grasp. The observable universe is not the whole universe. It is only the part we can see, the part whose light has had enough time to reach us. A bubble, a horizon, a shoreline at the edge of a far greater ocean we can never fully witness. Everything beyond that boundary, if beyond is even the right word, is hidden not by darkness but by the speed of light itself and the relentless expansion of space. There are regions of the cosmos so distant, so far removed, that their light will never reach Earth, not even in the lifetime of the universe. And somewhere past that unreachable frontier, the true universe continues, perhaps infinitely, perhaps in ways no human mind is built to comprehend. By the end of this journey, you'll understand why cosmologists speak of cosmic horizons with the same reverence that ancient sailors spoke of the edge of the world. You'll see why some physicists believe the observable universe is only one patch in a far larger mosaic, and you'll feel the gravity of a humbling realization: the majority of reality may lie forever outside our reach. Before we go any further, if you enjoyed deep dive explorations into cosmic mysteries, existential puzzles, and the mind-stretching limits of science, a quick like or subscribe really helps the channel grow. And if you tap the notification bell, you won't miss the next voyage beyond the stars. Thank you. Now let's begin at the boundary of everything we can see. Imagine sailing across an endless ocean and reaching a coastline, not because the sea ends, but because your map runs out. That is what the observable universe truly is. Not the end of space, but the end of what we can perceive. The boundary of this cosmic map is set not by distance alone, but by time. Light travels at a finite speed, and the universe has a finite age, about 13.8 billion years. That means we can only see objects whose light has had enough time to reach us. But here's where the picture becomes astonishingly counterintuitive. The edge of the observable universe isn't 13.8 billion light-years away. It's roughly 46 billion light-years in every direction. This is because the universe has been expanding the entire time that light has been traveling toward us, like the ground stretching beneath your feet, even as you walk. Beyond that edge, the universe does not stop. Galaxies continue, space continues, the cosmic web stretches on, but their light can never outrun the expansion enough to reach us. It's not a matter of distance, it's a matter of physics. Space itself is expanding faster than the speed of light in those distant regions, pulling galaxies away from us at velocities that lock them forever outside our view. So when we look at the night sky, we're not seeing a cosmic whole. We're seeing a spherical, expanding bubble of information, a fragment of a much larger reality. The observable universe is like a lantern held in the dark, illuminating only a limited volume, while shadows stretch infinitely outward. And the most mind-bending part, every observer on every planet around every star has their own observable universe, a different bubble, a different map, a different limit. The cosmos looks different from every point within it. The true universe is something we only glimpse through the narrow window of what light has allowed us to see. To understand what lies beyond our cosmic boundary, we must understand the horizon itself, not a physical wall, but a limit defined by relativity. Imagine watching a ship sail into the distance until it disappears behind the Earth's curvature. The ship still exists, still moves, still goes on with its journey. You simply cannot see it anymore. The cosmic horizon works the same way, except instead of curvature, it is cosmic expansion that hides distant regions from view. Space is not static. It stretches, it grows. Every second, more distance erupts between galaxies. The farther away something is, the faster it moves from our point of view, and beyond a certain distance, the expansion becomes so dramatic that light emitted toward us can never close the gap. That distant region becomes permanently hidden, not because it is dark, but because it is receding faster than light can travel. This introduces a haunting truth. There are galaxies, entire clusters, perhaps even civilizations whose light will never reach us. Not now, not ever. They are not far. They are beyond reach by definition. This horizon is not fixed. It changes as the universe ages, meaning the cosmic shoreline we see today is different from the one a billion years ago, and different from the one that will exist a billion years from now. The universe is constantly redrawing what can and cannot be known. And even more unsettling, the regions that lie beyond our view may outnumber what we can see by factors we can't meaningfully express. If the universe is truly infinite, and all evidence suggests it might be, then the observable universe is no more significant, proportionally, than a single drop of water in all the oceans of Earth. We are living inside a cosmic bubble, not because space is small, but because reality is too vast for light to reveal. Once we accept that the observable universe is only a limited sphere carved out by light and time, the next question becomes unavoidable. What lies beyond? Cosmology offers a radical possibility. The regions beyond our horizon look much like the ones we can see. The same cosmic web of galaxies, the same large-scale structure, the same physics, the same matter woven into filaments and voids, but extending on, without edge, without center, without boundary. And yet, there are signs that the unobservable universe may not be exactly like ours. Some come from subtle anomalies in the cosmic microwave background, the faint afterglow of the Big Bang, small patterns, strange alignments, and temperature irregularities that don't fit neatly within our local cosmic bubble. Some theorists argue these could be imprints of structures outside our observable universe, regions whose gravitational influence lightly tugged on our own bubble during the early expansion. Another clue lies in the concept of dark flow, a peculiar directional motion observed in distant galaxy clusters. Though debated, some interpretations suggest they are being pulled by something outside our horizon, something massive, something we cannot see. Speculative theories propose that space may be infinite, that there may be countless volumes beyond our cosmic region, far more than we could ever map. If true, then our observable universe is not special. It is simply the part light has revealed so far. In this view, we are not observers at the center of anything. We are residents of a tiny, illuminated pocket in a cosmos that extends far beyond our ability to measure. And whatever lies outside our bubble remains hidden, not by secrecy, but by the laws of physics themselves. To understand what might lie beyond the observable universe, we must journey back to a moment so early, so incomprehensibly small, that our usual notions of space and time fall apart. This moment is the era of cosmic inflation, a fraction of a second after the Big Bang, when the universe expanded faster than the speed of light, not because objects were moving through space, but because space itself was stretching. During this inflationary burst, quantum fluctuations, tiny random variations in density, were blown up to cosmic scales, seeding the structure of the universe we see today. But inflation also carries a profound implication. If the universe grew enormously in that instant, far more than our horizon allows us to observe, then the cosmos is almost certainly vastly larger than the portion we can see, perhaps infinitely so. This means the observable universe is just one patch of a much greater expanse. Outside our cosmic bubble may lie regions of space far beyond our horizon, never visible due to inflation stretching them away faster than light can travel. These regions may contain galaxies similar to ours, or arrangements of matter we can scarcely imagine. They may follow the same physical laws or different ones. Hints of this hidden universe occasionally appear in our measurements. Subtle asymmetries in the cosmic microwave background, unexpected alignments, and the debated phenomenon known as dark flow all raise the possibility that something enormous, beyond our observable limit, tugs gently on the cosmic fabric. Even if inflation created a universe that is smooth on large scales, It also implies that we can never see most of it. The majority of the cosmos lies forever outside our view, separated from us by expanding space. We live within a tiny island of information, carved out by the finite speed of light, surrounded by a reality whose true extent remains unknown. If the implications of inflation are correct, then our observable universe is not the universe. It is merely the part we are permitted to see. As astronomers examine the large-scale map of the cosmos, they notice something both haunting and tantalizing. Some galaxy clusters appear to be drifting in a particular direction, as if influenced by something outside the observable universe. This phenomenon, often called dark flow, has sparked intense debate. While its interpretation remains uncertain, it raises a startling possibility that the universe beyond our horizon contains structures so massive that their gravitational imprint extends into our visible region. If such structures exist, we cannot see them directly. We cannot measure their light or map their shape or trace their motion. Instead, we infer their existence from the faint and indirect ways they tug on space itself. These tugs disrupt the perfect randomness expected in the cosmic microwave background and subtly influence the motion of galaxy clusters near the observable edge. Other anomalies, strange temperature alignments, the so-called axis of evil, and patterns that defy the assumption of perfect isotropy, whisper of something beyond what our instruments can reach. None of these signals are conclusive, but together they paint a picture of a universe that may be structured on scales far larger than our cosmic bubble. Some theories suggest that the universe may be infinite, with no center and no boundary. In such a universe, every region would contain galaxies, stars, and cosmic structures stretching endlessly. Others propose a universe that is finite, yet unbounded, like the surface of a sphere but in higher dimensions, so that traveling far enough would eventually return you to where you began, though not in any sense we find intuitive. Whatever the case, one truth emerges. The region we inhabit is far too small to reveal the universe's true shape. We see only one patch of a cosmic mosaic whose full pattern extends far beyond the reach of light. The unseen universe is not empty. It is simply beyond our ability to witness. If the universe is infinite, then the implications are staggering. Infinity is not simply a lot of space. It is a different category of existence altogether, one in which everything that can exist does exist somewhere. In an infinite cosmos, the observable universe becomes a microscopic fragment, a grain of sand in a desert with no edges. In such a universe, galaxies stretch outward without end. Every direction, every line, every path extends forever. There are no borders, no cosmic edge, no final frontier where space stops or transitions into something else. The universe does not curve back on itself, nor does it fold into a finite structure. It simply continues. This concept reshapes our understanding of cosmic density. If space is infinite, the number of galaxies is infinite. The amount of matter is infinite. And statistically, even worlds like Earth, complex, habitable, and capable of hosting conscious beings, should appear not once but countless times, not as science fiction copies but as a consequence of infinite variation in an unbounded universe. Yet infinity complicates everything. It makes it impossible to define an average cosmic environment. It makes our measurements of matter density local rather than global. It means the universe we see may be typical or extremely unusual, without giving us any way to know which. But perhaps the most humbling implication of infinite space is this: our cosmic bubble is not special. It is one region among countless billions, each one equally real, equally vast, equally filled with galaxies and worlds and possibilities we will never encounter. Infinity strips away the illusion of centrality. It reveals a universe in which human perspective is not merely small, but infinitesimal. Once we accept that the observable universe is only a tiny fragment of a far larger whole, an even deeper question emerges. What if our entire universe is just one among many? The multiverse hypothesis proposes that reality may not be a single, continuous expanse, but a collection of universes, each with its own laws, its own initial conditions, its own cosmic histories. Some may resemble ours, others may differ in ways so radical that human intuition would fail instantly. In certain inflationary models, our universe is merely a bubble in a vast, ever-expanding cosmic foam. New universes may form continuously, budding off from an inflating backdrop like droplets separating from a turbulent sea. These bubble universes never collide, never interact. Each is sealed off by its own expanding space. The observable universe becomes just one patch within a boundless, unreachable landscape. There are other interpretations. In quantum cosmology, every possible configuration of reality exists as a branch of a colossal superstructure of possibilities. In this view, every outcome, every event, every deviation becomes a separate universe, parallel realities layered beyond our perception. For physicists, the multiverse is not a whimsical escape from explanation, but a potential solution to puzzling facts about our universe. Why does the strength of gravity have its particular value? Why do the laws of physics allow stars to form and chemistry to exist? Why is our universe so remarkably fine-tuned for complexity? If countless universes exist, each with different laws, then ours may simply be one of the rare few where conditions happen to align in the right way. Yet beyond the scientific implications lies a deeper, more personal one. If the multiverse is real, then our universe is not the grand stage of all existence. It is a single theater among many, a single script performed on countless unseen stages. Our story, while precious, is not the only one reality is telling. In contemplating the multiverse, we grapple with the possibility that reality is far bigger, far stranger, and far more layered than we ever imagined. Most people take space for granted. We live in 3 dimensions: length, width, height, and time flows forward. These 4 dimensions define every experience we have. Yet theoretical physics suggests that space may contain more structure than our senses allow. Hidden within the fabric of the universe may lie extra dimensions, curled up or stretched out in ways that defy intuition. Some theories propose that the universe has more than the 3 spatial dimensions we perceive. These extra dimensions may be incredibly small, folded into shapes far tinier than atoms, or they may extend outward in directions inaccessible to us. They could influence gravity, particle physics, and the behavior of the universe itself, even if we cannot directly perceive them. One compelling idea is brain cosmology, which envisions our universe as a 3-dimensional membrane floating within a higher dimensional space called the bulk. Everything we know, galaxies, atoms, light, even the fundamental forces, could be confined to this membrane. Gravity, however, might leak into the extra dimensions, hinting at why it is so much weaker than the other forces of nature. If this picture is correct, other brains may drift alongside ours in the higher dimensional bulk, parallel universes separated not by distance but by dimension. They may be unimaginably close in a direction we cannot point to, containing their own galaxies, their own physics, their own histories. These ideas are not science fiction. They arise naturally from attempts to unify quantum mechanics and gravity, yet they challenge the deepest assumptions we have about reality. Space may be shaped in ways we cannot visualize. Distances may not be absolute. Fundamental forces may be shadows of higher dimensional interactions. In a universe with extra dimensions, our observable world becomes a projection, a slice of a much larger, richer structure. The cosmos extends not only beyond our horizon, but beyond our dimensional comprehension. As we push further into these speculative realms, multiverses, higher dimensions, infinite spaces, we approach a boundary not set by physics, but by the limits of human thought. There comes a point where the scale, complexity, and abstraction of the universe exceed the capacities of the brains that evolved on a small, fragile planet orbiting an ordinary star. Every scientific instrument ever built, every telescope ever pointed at the sky, every equation ever written works within the narrow limits of what can be measured. Beyond the observable universe lies a region permanently inaccessible to observation. Beyond the dimensions we can detect lie hypothetical realms we can barely describe. Even the laws of physics may change in regions we will never reach. At this frontier, science and philosophy begin to blur. Theories become maps of landscapes we cannot explore. Mathematics becomes a form of storytelling. Concepts like infinity, extra dimensions, and universe-generating inflation stretch our intuition until it cracks. Yet this does not diminish the pursuit, it elevates it. Humanity has always stood at the edge of comprehension, gazing into mysteries larger than itself. Ancient people stared at the stars without knowing what they were. Physicists probed atoms long before understanding their inner structure. Today, cosmologists confront a reality whose scale dwarfs galaxies and timelines beyond imagination. The observable universe is not the limit of existence. It is only the limit of what we can currently know, and the truth beyond that boundary, whatever it is, remains one of the most profound and humbling questions ever asked. We stand on the shoreline of a cosmic ocean, aware that most of its waters lie forever beyond sight, yet drawn inevitably toward the horizon. Even though we cannot see beyond the observable universe, the edge itself holds subtle clues, small distortions, patterns, and remnants of ancient processes that ripple across the visible cosmos like echoes from beyond our horizon. These clues don't reveal what lies outside, but they hint that the universe is influenced by more than we can directly observe. One of the richest sources of information is the cosmic microwave background, the afterglow of the Big Bang. It is a faint, nearly uniform field of radiation that blankets the sky, but it is not perfectly smooth. It contains minute temperature fluctuations, hot and cold patches only thousandths of a degree apart. These tiny variations map the seeds of galaxies, the blueprint of cosmic structure. Yet among this pattern lie anomalies, unexpected alignments, regions that appear slightly larger or smaller than predicted, and temperature asymmetries that defy easy explanation. Some cosmologists argue that these could be hints of structures beyond our horizon, massive concentrations of matter tugging on the early universe before inflation pushed them out of sight. Others see in these distortions the faint signature of alternate regions of spacetime, each shaped by initial conditions we can no longer access. We also investigate the distribution of galaxies, looking for distortions in their motion or arrangement that might point to forces outside our bubble. If distant galaxy clusters appear to drift in a specific direction, or if large-scale structure shows unexpected coherence, it could indicate gravitational influences arising from unseen regions. These observations don't give us a map of what lies beyond. They give us a whisper, a suggestion that the observable universe is not an isolated island, but part of a larger tapestry whose threads stretch into the unseen. At the horizon, we touch the boundary between knowledge and speculation, and in that boundary we find questions that grow only deeper the longer we study them. As we push beyond the limits of measurement, physics becomes less about direct observation and more about the power of theory. When we cannot see what lies past the cosmic horizon, we turn to mathematics, logic, and the consistency of physical laws to guide us. Theories of inflation, quantum mechanics, higher dimensional geometry, and string theory become our tools, not because they reveal the unseen universe directly, but because they provide frameworks that remain coherent even when extended beyond observable limits. Theoretical physics steps into the void, left by the failure of our instruments. It constructs models of universes far larger than the one we can observe. It imagines dimensions invisible to our senses. It explores cosmic beginnings earlier than physical evidence can reach. In doing so, theory becomes both an extension of science and an encounter with the philosophical. The universe, at its deepest level, may exist in ways that no experiment could ever confirm. Yet these theories are not arbitrary. They are anchored to the parts of the universe we can see. They must agree with the cosmic microwave background, galaxy surveys, gravitational waves, and the structure of space-time revealed by relativity. A theory that describes the unseen must still match the visible. This interplay between what can be measured and what must be imagined defines the frontier of modern cosmology. When we ask what lies beyond our horizon, we are asking questions that stretch theory to its breaking point. Questions about the origin of space, the shape of time, the nature of existence itself. Here, science becomes a form of exploration into landscapes no human will ever visit. We rely on equations as our ships and logic as our compass. And even though we may never confirm these models, they illuminate possibilities that reshape how we understand the universe and our place within it. When we consider the scale of the universe beyond what we can observe, the limits of our knowledge become unmistakably clear. The observable universe, enormous as it appears, is restricted by the speed of light and the expansion of space. Everything outside that boundary remains fundamentally inaccessible. No telescope, no future technology, no clever trick of physics can bring those regions into view. They exist independently of our ability to detect them. This boundary forces us to acknowledge that most of the cosmos lies outside our reach. Whether space extends infinitely or ends in some way we cannot yet define, the portion we can study directly is only a fragment. The laws of physics we test and measure apply within this fragment. Beyond it, we cannot be certain. If the larger universe contains different structures, conditions, or even different physical laws, those realities would remain hidden from us. Scientific models attempt to extend our understanding past the observable horizon, but they rely on extrapolation. They assume the patterns we see continue into regions we cannot access. This may be correct, or it may not. The true structure of the universe, its size, its shape, its contents, could differ dramatically from what our observations suggest. Even our most advanced theories remain constrained by the part of the universe we can test. They describe possibilities, not confirmed features. The reality beyond our horizon may align with these ideas, or it may exceed them in ways we cannot anticipate. In this sense, our understanding of the universe is incomplete by design, limited by the very nature of space-time. The observable universe is therefore not the totality of existence, but the limit imposed on what we can directly study. Everything beyond it persists independently of our measurements, forming a realm that remains outside our observational reach. Whatever lies there, whether familiar or unknown, exists without revealing itself to us.